Imagine capturing the entire energy output of the sun, not with a single machine, but with a structure so vast it would surround an entire star. This idea is called a Dyson Sphere, one of the most extreme concepts ever proposed by physics, and according to the laws of science, it isn't completely impossible. But building it would demand a scale of engineering humanity has never attempted so massive. It could require dismantling an entire planet. Now, that sounds like pure science fiction, right? Something only a civilization thousands of years ahead of us could ever attempt. But what if we told you that astronomers have found a real star, thousands of light years away, that is behaving exactly like it is being built right now? Meet Kepler 452 and Tabby's star. Both are sun-like stars located at roughly comparable distances from Earth. Yet Tabby's star behaves in a way that immediately stands out, because over the past few years its brightness has dimmed irregularly and unpredictably, something we do not observe in Kepler 452. Astronomers pay close attention to such anomalies for two reasons. First, unexplained dimming often points to new or poorly understood cosmic phenomena. And second, a well-known speculative idea suggests that if an advanced civilization exists, one possible signature could be large-scale engineering projects around stars, such as a hypothetical energy-harvesting megastructure called a Dyson Sphere. Now, to be clear, this is not the scientific consensus in Tabby's star's case, but the idea gained attention because the dimming pattern does not neatly match planets, dust clouds, or typical stellar cycles. The sheer scale involved is almost beyond comprehension, since even planets passing in front of stars are negligible in size, and a full Dyson-like structure around our own sun would need to extend out to roughly Earth's orbit, forcing a serious question rather than a sensational one. Could any civilization ever command the materials, energy, and engineering precision required for such an undertaking? And if humanity were to attempt something similar in the distant future, what fundamental technical limits would we encounter? And could we realistically overcome them at all? To understand where this idea came from, consider how visionary thinking has always preceded technology. 6 centuries ago, Leonardo da Vinci sketched a working concept of a helicopter despite the absence of engines or airplanes, drawing inspiration from birds he observed in nature. But the Dyson Sphere is different because nothing even remotely similar exists around us, which makes its origin even more intriguing. The story begins in the mid-1950s, when most satellites relied on batteries charged on Earth and were effectively abandoned once those batteries drained, until NASA launched Vanguard 1 in 1958, the first satellite capable of recharging itself in space using solar panels. And while this mission had nothing directly to do with alien megastructures, it sparked a profound idea in the mind of physicist Freeman Dyson. If a satellite could orbit Earth and continuously harvest solar energy, then, in principle, an advanced civilization could scale this concept up by placing vast numbers of solar collectors around a star, gradually linking them into a spherical swarm and extracting energy directly at the source, instead of relying on the tiny fraction that naturally reaches a planet's surface. Scientists already understood that only a small portion of a star's total output can ever be intercepted by a single planet, and Dyson's proposal was essentially a logical leap. If energy is the foundation of progress, then the most advanced civilizations would inevitably move closer to their stars, capturing as much power as physics allows. And it was this sober, engineering-driven line of reasoning, not science fiction, that first placed the radical idea of enclosing a star into serious scientific discussion. Even with today's technology, our most advanced solar panels convert only about 20% of incoming sunlight into usable electricity. Yet if energy were captured from a star on all sides, rather than on a single planet, the total yield would still increase by several orders of magnitude, enough, in theory, to power human civilization for timescales measured in trillions of years, and it was precisely this staggering energy advantage that first made the idea take shape in Freeman Dyson's mind. The logic is straightforward. If a civilization continues to grow, it will eventually reach a point where the limited sunlight reaching its home planet is no longer sufficient, forcing it to harvest energy closer to the source. And once that possibility is acknowledged, it becomes reasonable to ask whether an advanced extraterrestrial civilization might already be doing the same. This insight transformed the Dyson Sphere from a purely theoretical engineering concept into a powerful tool for the search for intelligent life, because the presence of such a structure would leave a detectable signature in the form of a star that appears unnaturally dim, giving astronomers a concrete direction rather than blind speculation. And that shift in thinking was revolutionary at a time when the hunt for extraterrestrial intelligence had little observational focus. Decades later, in 2015, NASA identified a star whose brightness dropped below expected limits, reigniting speculation about artificial megastructures. But before leaping to extraordinary conclusions, the real question must be confronted. Using even our most optimistic modern technology, is constructing something as vast as a Dyson Sphere physically and practically possible at all? And what insurmountable challenges would stand in the way if humanity ever attempted it? According to Stuart Armstrong from University of Oxford, Freeman Dyson's original concept is fundamentally impractical, a conclusion he reached after years of research on how humanity might expand beyond Earth and colonize other regions of space. When Armstrong closely analyzed the Dyson Sphere model, he identified two critical flaws. First, the sheer material requirement, since constructing a rigid shell around a star would demand a mass comparable to that of Jupiter, an almost incomprehensible amount of matter considering that Jupiter could contain over 1,000 Earth-sized planets. And second, the issue of stability, because even a minor asteroid impact could destabilize the structure, causing catastrophic failure and sending large portions of the sphere spiraling into the sun. This analysis dealt a serious blow to the idea of a solid Dyson Sphere. But it did not end the concept altogether, because Armstrong also proposed a more realistic alternative. Rather than enclosing a star with a single rigid shell, an advanced civilization could deploy countless independent solar collectors in orbit, each operating separately and safely, a design he termed the Dyson Swarm, which preserves the original goal of harvesting stellar energy while avoiding the extreme material demands and structural fragility that make the classic Dyson Sphere nearly impossible in practice. In Armstrong's refined model, the Dyson Swarm would consist of tens of millions of independent solar collectors arranged in vast orbital rings around the Sun, with large reflective surfaces concentrating sunlight onto high-efficiency solar cells, converting it into electricity, and then transmitting that energy toward Earth as tightly focused microwave beams. Microwaves are critical here because only visible light, microwaves and radio waves can reliably pass through Earth's atmosphere. Radio waves would interfere with communication systems, and visible light scatters too easily, making microwaves the most practical carrier for large-scale power transmission, which could then be safely converted back into usable energy on the ground. The major advantage of this design is resilience, since a collision with an asteroid would destroy only a single collector rather than triggering a catastrophic collapse of the entire system, neatly eliminating one of the biggest weaknesses of a solid Dyson Sphere. Yet this solution immediately exposes a deeper problem, the question of construction. Because before a single watt of energy ever reaches Earth, humanity would need to manufacture and launch those millions of satellites. When Stuart Armstrong calculated the raw material requirements, he found that even this distributed swarm would demand an almost planetary scale of resources comparable to the mass needed for a full Dyson Sphere, implying that Earth alone could never supply it, and that the only realistic option would be large-scale mining of nearby worlds like Mercury and Mars, along with the development of off-world industrial infrastructure capable of manufacturing and assembling solar collectors far beyond anything humanity has ever attempted. Even after manufacturing the collectors off-world, the challenge would be far from over, because launching millions of panels into precise solar orbits would require massive spaceports and propulsion infrastructure near the Sun itself, meaning such a project would only become realistic once humanity is living and industrializing other planets. Many scientists estimate that reaching this level of technological and societal maturity could take on the order of 1,000 years. which is why most researchers argue that building a true stellar megastructure, whether a Dyson Sphere or even a Dyson swarm, is extraordinarily difficult for humans and likely for alien civilizations as well. And this is precisely why the unusual dimming of Tabby's star observed in 2015 is now widely believed to have a natural explanation. Most likely, large clouds of dust blocking its light rather than any artificial structure. A conclusion reinforced by a similar case involving Betelgeuse, whose apparent unnatural dimming was later traced to a massive dust plume. Even if we imagine a future where technology overcomes today's limits, a deeper concern remains: energy economics. Because some calculations suggest that extracting the raw materials from Mercury alone could consume an enormous fraction of the energy such a system would produce, and when the additional costs of mining Mars, manufacturing components, and maintaining the infrastructure are included, the balance could become negative, like spending $20 to earn 10, implying that with our current understanding, the effort may yield less energy than it consumes. Though it is also entirely possible that this conclusion reflects the limits of present-day technology rather than the true potential of a far more advanced civilization. I'd love to hear your thoughts in the comments. Do you believe structures like Dyson spheres could exist in the future? Or do they belong permanently to the realm of theory? And if you learned something new today, don't forget to like, subscribe, and stay curious and keep learning.